Here we have an example to compute the frequency response. So in Python we can use from the SciPy signal the function frec_z to compute the frequency response. So in our example, if we choose our pole to be 0.9, so our A1 coefficient will be 0.9. So we need to make some manipulation to put the vectors in a form that is accepted by the frec_z. So we have that our zeros will be given by this vector b equals 1, and our poles will be here in this vector a. So this is our coefficient a0 and a1, and it needs to be negative when our pole is positive. So this is the way to create our vectors to use with the frec_z. So here we are importing our functions. We will use frec_z from SciPy signal. We use matplotlib to plot, and we use NumPy to handle arrays. So we're just defining here the arrays that we said here. So this is A and B, and here we are calling the frec_z. We're giving as an argument the B vector, the A vector. This is the number of the frequencies that these frec_z functions will calculate, the frequency response, and whole means that we'll only look at the positive part of the frequency response. So we're assuming that we have real values, so the positive and the negative parts are symmetric, and we are using this whole. If we set it to true, then it will compute also for negative frequencies. So this frec_z will return a vector with the frequencies and a vector, a complex vector with our frequency response. So now we can plot this digital filter frequency response. So two subplots. On the first subplot we'll have the magnitude dB, and on the second we'll have the phase. So this is what we're doing here. This is the first plot, and we want in dB, so we're multiplying by 20 times the log base 10 of the absolute of the frequency response. So here we are getting the magnitude, and then we are also plotting the phase using NP angle. So we're getting the phase from our complex frequency response, and we have here this magnitude and phase of our digital filter, and we can see that it has a low pass characteristic. So here in the horizontal axis we have the normalized frequency, so it goes from 0 to pi, where pi is the Nyquist frequency or half the sampling frequency. So it's clear here that this frequency response has a low pass characteristic. We can also plot the location of the zeros and poles in the complex z-plane. So first we need to calculate the poles and zeros. We can use the Python function np_roots. So we have this transfer function here, and then the roots expect as np_roots expects as an argument the order coefficients of our polynomial in z to the power of -1. That makes it also compatible with L filter, so we can use this np_roots to have our pole positions using np are the roots of the vector A, and the zeros roots of vector B. So this is, we're defining here a function that's called z-plane that's going to plot the poles and zeros. So the poles will be marked with an X, and the zeros will be marked with a circle. As this is our transfer function, we don't have any zero, and we'll have a pole. So if b is equal to 0.9, we have a pole at 0.9. So what we're doing here, we are plotting a unit circle, just configuring the plot to have this y-axis here in the middle. This will be the imaginary part, this will be the real part, and then we're calling the z-plane with the roots of p that we defined earlier here in the roads of A, and we have this complex z-plane, and here we have our pole at 0.9. So zeros are marked with a circle and poles here are marked with an X, and here we see the pole at the location z equals to 0.9. So in general, the closer a pole is to the unit circle, the larger is the corresponding peak in the magnitude of the frequency response at a normalized frequency identical to the angle of the pole to the origin. So this can be seen by turning the z transform into a DTFT by replacing z by e to the power of j omega. Hence, the frequency response is obtained by running on this unit circle, and omega is our angle and also the normalized frequency. So the closer we get to a pole, the higher the magnitude of the frequency response becomes. And this is opposite for zeros. So the closer we come to a zero, the smaller the magnitude of the frequency response becomes. So here our pole has an angle of 0 degrees, and in this example we can indeed observe a peak in the magnitude response at a normalized frequency omega equals to 0. So we have it, omega equals to 0. So the filtering operation itself works similar in MATLAB, Octave or Python in the time domain. So the function in Python is lfilter in scipy. So given an input signal in the vector x and a filter coefficients in vectors a and b, the filtered output y, we can use the lfilter. So y will be the lfilter. We pass it the b and a vectors, and here is the input vector.